Hi again, this is Simon. For the third part of this tutorial, we are going to discuss applications of VAEs in audio and speech processing. Let ST denote the time frame at index T of an audio signal in the short time Fourier transform domain. So we consider the following non-stationary Gaussian model, which is quite standard in the literature and which can be traced back to this well-known paper by Ephraim and Mala. So ST is considered as a Gaussian random vector, complex Gaussian random vector with a zero mean and a diagonal covariance matrix. The diagonal of this covariance matrix represents the local power spectral density of the audio signal. We can interpret this diagonal of the covariance matrix, this vector of variance coefficient, as the power spectrogram somehow of the signal, because maximum likelihood estimation of the variance coefficients is given by the STFT power spectrogram of the signal. This notation here denotes element-wise exponentiation. The variance in the literature is usually further constrained with a model to encode specific spectrotemporal characteristics of audio signals. Let's see a few examples of models that have been used within this spectrotemporal variance modeling framework. We can mention structured sparsity inducing priors that have been employed for modeling tonal and transient sounds, for enforcing vertical or horizontal lines within a spectrogram. Then, for the past 10 years, non-negative matrix factorization models have been very popular for modeling or learning temporal repetitions of spectral templates in audio spectrograms. More recently, variational autoencoders have been employed for learning spectral structures independently over the time frames of an audio signal. And even more recently, recurrent variational autoencoders, the RVAE model that we have discussed before, have been employed for learning spectrotemporal structures. As the variational autoencoder shares some similarities with NMF that we will discuss a bit later, let's first present a bit in more details this NMF-based variance modeling. So in this model, the variance at a given time frame t is structured as the product of two non-negative quantities. W, a dictionary matrix of spectral templates, and HT, which indicates how those templates are activated at a given time frame t. The dictionary matrix contains capital K templates. We call K the rank of the factorization, and it also corresponds to the number of coefficients in HT. This rank of the factorization is usually chosen such that the number of parameters in the NMF model is smaller than the total number of time frequency points. So you have in this figure an example of an NMF decomposition of a piano signal, which contains two piano notes that are first played individually and then simultaneously. We see that the dictionary matrix here contains the spectrum of each note, and the rows of the activation matrix indicate how and when the two notes are activated. It can be shown that maximum likelihood parameters estimation in this NMF model is equivalent to solving the following optimization problem, which involves the Itakura-Saito divergence between the power spectrogram of the signal and the NMF factorization. Now, let's discuss the VAE-based variance modeling. In this model, the variance at a given time step t is provided by a neural network, a feed-forward fully connected neural network, which takes as input a low-dimensional random vector zt, which follows a very simple Gaussian prior with zero mean and identity covariance matrix. So this network here corresponds to the decoder network in a VAE. Similarly to NMF, maximum likelihood parameters estimation in this VAE-based variance model is equivalent to solving an optimization problem that involves the Itakura-Saito divergence. We have an additional expectation here because ZT is a random variable, and this expectation is taken with respect to the inference model that approximates the intractable exact posterior. And as we have seen, this inference model is implemented with an encoder neural network in the VAE framework. And the parameters of this encoder network should also be estimated. So actually, this optimization problem here corresponds to the maximization of the reconstruction accuracy term in the VAE objective function, the elbow or the VLB as we called it before. So to sum up, we can make a parallel between NMF-based variance modeling and VAE-based variance modeling. For NMF, the variance at a given time step t can be seen as a linear function of a low-dimensional vector, which is the vector of activation coefficients ht. W corresponds to the parameters of this function. For VAE, the variance is a nonlinear function of a low-dimensional vector, this vector being zt. For NMF, the number of trainable parameters is constrained by the rank of the factorization. If we want to give a bit more flexibility in the model by increasing the number of parameters, we will have to increase the rank of the factorization, so the number of columns in W, which will also increase the number of coefficients in the activation vector ht. For the variational autoencoder-based model, the number of trainable parameters is somehow free because we can choose an arbitrary architecture for the decoder network while not touching to the dimension of the latent vector zt. We have seen that for both NMF and variational autoencoder, estimating the model parameters in the maximum likelihood sense is equivalent to solving an optimization problem based on the Itakura-Saito divergence. Finally, for the NMF model, it's really easy to interpret the parameters, the decomposition, as we have seen with the piano example. For the variational autoencoder, interpreting what properties of the signal are encoded in the latent vector zt is still an open problem. For the variational autoencoder-based variance model, the STFT timeframes of the audio signal are not only conditionally independent given zt, but they are also marginally independent. So the joint distribution of a sequence of STFT timeframes can be written as the product of marginal distributions over each individual timeframes. This is of course a limitation when modeling audio and speech signals, but fortunately it can be overcome by using a dynamical variational autoencoder. So we come again to the general chain rule formula that we have seen when defining the general class of DVAE models. So ST here is used instead of XT that we were using before. In this chain rule, we have again a product over the time frames of two distributions, an observation or emission model distribution over ST, and a transition model distribution over ZT. So to use a dynamical variational autoencoder within this variance modeling framework that we have just presented, we should define the emission distribution as a complex propagation distribution with a zero mean and a diagonal of the covariance matrix, which is provided by a recurrent neural network. This choice implies that the Itakura-Saito divergence will be involved in the reconstruction accuracy term of the VLB that will be optimized to learn the DVAE model parameters. The transition distribution over ZT can here be defined arbitrarily. So let us now move to the application of DVAEs for analysis resynthesis of speech signals. The task is the following. we want to analyze and resynthesize speech power spectrograms, which, using a variational autoencoder, corresponds to an encoding-decoding process. We compare 6 different dynamical variational autoencoder models that we have presented before and a vanilla variational autoencoder. All the models are reformulated in the variance modeling framework that we have just presented. Importantly, we try to make the same network design choices for the different models that we compare whenever possible. Therefore, rather than using the same hyperparameters as presented in the original papers, we set some of them to be equal among all models. To train and test the models, we use the Wall Street Journal dataset, which contains 25 hours of training data, 2 hours of validation data, and 1.5 hours of test data. It consists of read speech sampled at 16 kHz. The input dimension of the variational autoencoder and consequently also the output dimension is equal to 257, while the latent space dimension is 16. To evaluate the models, we compare the reconstruction qualities in the waveform domain. So time domain signals are reconstructed from the power spectrogram using the original phase of the signal, the oracle phase, and inverse STFT with overlap add. We use different metrics, the root mean squared error, for which the lower the better, the perceptual evaluation of speech quality, the best measure in between -0.5 and 4.5, for which the higher the better, and the short time objective intelligibility measure, the STOI measure, in between 0 and 1, for which also the higher the better. We first compare all the models that consider an IID prior over the latent vectors ZT. It includes the standard vanilla variational autoencoder, the RVAE model, and STORN. The star here indicates the models that have an inference distribution which is compliant with the structure of the exact posterior distribution. We first observed that RVAE provides an improvement compared with the standard variational autoencoder. The non-causal version of RVAE provides a slight improvement compared with the causal version in terms of PESC measure. We also see that STORN clearly outperforms RVAE. STORN has actually a much more complex observation model compared with RVAE, as it is actually an autoregressive model. ST is generated not only from Z1 to T, but also from the previous observation vectors S1 to T-1. And apparently, having such an autoregressive generative model for ST is useful. The inference model in STORN is simplified compared with the exact posterior distribution in terms of temporal dependencies between the random variables. It is reasonable to assume that taking into account the exact posterior dependencies within the inference model of STORN would lead to even better performance. Next, we can compare the two models that are close to state space models in terms of temporal dependencies between the observed and the latent variables. Those two models are DMM and DSAE. Actually, the generative models in DMM and DSAE are close, as can be seen from this factorization here. A key difference between the two is that the inference model in DMM is compliant with the structure of the exact posterior distribution, while it is not the case for DSAE. And we see that the performance of DMM is clearly above the performance of DSAE in our experiments here. So we can assume that having an inference model whose structure corresponds to the structure of the exact posterior in terms of dependencies between the observed and latent variables is very important. If we now compare the performance of DMM with the performance of STORN, we can think that having temporal dependencies on the latent variables, as it is the case for DMM, is more important than having a powerful autoregressive generative model over the observations st. But of course, we can have both. And this leads us to the next two models, VRNN and SRNN, which are the most complex generative DVAE models that we have reviewed today. As we can see from the table of results, SRNN outperforms VRNN, and again, the inference model in SRNN corresponds to the structure of the exact posterior distribution. So this may also explain the difference between the two models. We have already discussed the importance of the implementation of temporal dependencies between random variables using RNNs in DVAEs. But let us illustrate this point with some numbers. In the experiments that we have just presented, the network architecture of our VAE was made more complex compared with the original model that was proposed in this paper last year. The motivation was to try to make some of the hyperparameters similar among all the compared DVAE models, as we have already explained. So the probabilistic model, the Bayesian network representing the dependencies between all the random variables, remained the same, but we changed the implementation of these dependencies using neural network. And we observed that this had a large detrimental impact on the performance. Of course, this may also be the case for other models, and tuning each model individually would be necessary. This table presents the analysis resynthesis performance of both causal and non-causal versions of our VAE with the original network and the more complex one. We see that by making the architecture more complex, we multiply the root mean squared error by almost a factor of 2. The PERSC measure goes from 3.47 for the original RVAE to 2.27 for the more complex version, and the STOI measure goes from 95% to 89%. The best performance is obtained with the original RVAE model in its non-causal form, which obtains results similar to VRNN, which is an autoregressive model, so with a more complex observation model. Here is an audio example where we compare the quality of the resynthesized speech signal using the original and the more complex RVAE models. This is the original speech signal.
That noise problem grows more annoying each day.
The reconstruction using the original RVAE model.
That noise problem grows more annoying each day.
And the reconstruction using the more complex network architecture.
That noise problem grows more annoying each day.
So now we move to an application of DVAEs in speech enhancement. So speech enhancement is the task that aims to recover a clean speech signal from the observation of noisy speech signal. Here we work in a single channel scenario, so we have only one microphone, and we consider a semi-supervised setup as defined in this paper by Paris-Marek Autoencoders in 2007. Semi-supervised here means something a bit different compared with the standard terminology in machine learning, because we are not going to learn from a dataset of pairs of noisy and clean speech signals. What we are going to do is the following. We will learn from a dataset of clean speech signals a prior over the clean speech. This prior will be either based on a standard variational autoencoder or based on RVAE. Then, at test time, when we observe a noisy speech signal, we will use an observation model based on non-negative matrix factorization. And the task will be to compute or to approximate the posterior distribution of the clean speech signal given the noisy speech signal. Let's start with the simplest speech prior based on the standard variational autoencoder. So the STFT frame of clean speech at time frame t is generated only from the latent vector z at time step t. The prior over ZT is again a standard Gaussian distribution with zero mean identity covariance. And the conditional distribution of ST given ZT is a complex Gaussian distribution. We are in the variance modeling framework, so we have a zero mean, and the diagonal of the covariance matrix is provided by a standard feed-forward fully collected neural network. As we have already discussed, the speech STFT time frames here are not only conditionally independent, but also marginally independent. For RVAE, we first remind the causal version of the model, where ST is not only generated from ZT, but also from the previous latent vectors Z1 to T-1, using a recurrent neural network to provide the variance in the generative distribution of ST. For the non-causal version of RVAE, ST is generated not only from the current and past latent vectors, but also from the future vectors. So the recurrent neural network that provides the variance here is bidirectional. During the training phase, we learn the parameters of all these neural networks, whether it be a feed-forward fully connected neural network for the standard VAE, or a recurrent neural network for the causal version of RVAE, or a bidirectional recurrent neural network for the non-causal version of RVAE. We learn the parameters of these networks on a dataset of clean speech signals, and here again we used the Wall Street Journal dataset. In the rest of the presentation of the speech enhancement method, we will only consider the non-causal version of the RVAE model, but the principles are the same for the causal version or even for the standard VAE-based speech prior. So now we are at this time, and the clean speech signal is therefore latent. What we observe is a noisy speech signal still in the STFT domain that we did not by XT. The generative model now includes an additional sequence, which is the sequence of noisy speech observations x1 to t. We have already defined the prior over ZT, the conditional distribution of ST given the sequence of latent vectors Z1 to T. What remains to be defined is the conditional distribution of XT given the clean speech ST. We consider that this conditional distribution is a complex Gaussian distribution centered around ST and with a diagonal covariance matrix structured by means of a non-negative matrix factorization model. So this is totally equivalent to considering that XT, the noisy speech, is equal to ST, the clean speech, plus a Gaussian noise with zero mean and a variance structured by means of an NMF model. So this is the so-called Itakura-Saito NMF model. Now that we have defined the clean speech and the noisy speech generative models, we need to perform inference in order to enhance the speech signal. Within this probabilistic framework, it consists in computing the posterior mean of the clean speech signal. That is, this expectation here of ST taken with respect to the posterior of ST given the complete sequence of noisy speech observations x1 to capital T. This expectation can be developed as a Wiener-like filtering involving a mask of coefficients between 0 and 1 that is applied element-wise to the noisy speech signal xt. This Wiener filter involves the latent random vectors z1 to t. That's why we have to take the expectation of the ratio here with respect to the posterior distribution of the latent vectors. We can interpret this expectation as an average over all possible realizations of the latent vectors according to their posterior distribution. So we are kind of averaging an infinite number of Wiener filters. the parameters theta s in the clean speech signal estimate have already been estimated during the training stage. They correspond to the decoder network parameters in the VAE or in RVAE. What is unknown here in this Wiener-like filtering is the posterior distribution of the latent vectors given the noisy speech signal, and also the NMF model parameters which characterize the noise. So typically, to estimate these two quantities, we can use an expectation maximization algorithm where we iterate two steps: the E step, where we compute the posterior distribution, and the M step, where we update the model parameters, here the NMF model parameters. The issue that we have here is that the true posterior distribution of the latent vectors Z1 to T is intractable due to nonlinearities. So we will use an approximate EM algorithm where in the E step we will have to approximate this intractable posterior distribution. We can consider three possibilities for the intractable E step. First, we can use Markov chain Monte Carlo methods to asymptotically sample from the true posterior. This is the approach that was originally proposed by Bando and Courters in a 2018 paper. This approach, however, is only proposed and in our case here implemented for the VAE-based speech model because extending it to RVAE is not straightforward. Second, we could use variational inference techniques where we would build a variational distribution Q over the latent vectors, which is an approximation of the true intractable posterior. And what we proposed in this paper last year is precisely to do this by fine-tuning the already trained RVAE encoder on the noisy speech signal X1 to T. So the parameters of this variational distribution are estimated by minimizing the Cal divergence between the variational distribution and the true intractable posterior. Finally, a last possibility would be to rely on a maximum a posteriori estimation of the latent vectors, which could be obtained using gradient-based optimization techniques, similarly as what was proposed in this paper by Kameoka and Courters. This technique can be interpreted as approximating the posterior by a Dirac delta function centered around the maximum a posteriori estimation of the latent vectors. For the experiments, as already mentioned, we use the Wall Street Journal dataset to learn the VAE or RVAE-based priors. For testing the speech enhancement algorithm, we create 1 hour and a half of synthetic mixtures of noisy speech signal by using clean speech signals in the test set of the Wall Street Journal dataset and noise signals from the QUT noise dataset. The test dataset contains 8 speakers that are different compared with the training set. The noise types are cafe, home, street, and car, and the SNRs are -5, 0, and 5 dB. We evaluate the speech enhancement quality in terms of scale invariant signal to distortion ratio, for which the higher the better. And as a reference, the SI-SDR, which is obtained by taking the noisy mixture as a speech estimate, is equal to -2.6 dB. We first compared the performance with the different approximate E-step approaches for the VAE-based speech prior, so the model without temporal modeling of the speech signal. We see that the MCMC algorithm obtains the best performance, which makes sense as the MCMC algorithm is able asymptotically to sample from the true posterior distribution. We also observe that the map and the variational approaches give similar results. For the causal version of RVAE, we observe a clear improvement compared with the standard VAE, which shows that taking into account temporal dependencies in the speech prior is useful. We also see that the variational approach obtains better results compared with the map estimation of the latent vectors. Finally, we cannot clearly see a difference with the non-causal RVAE model compared with the causal one. All the methods that we have compared so far are semi-supervised in the sense that the speech model is trained on a dataset of clean speech signals. But again, we insist on the fact that in all these methods there was no supervised training from pairs of clean and noisy speech signals. We know, however, that the state of the art in speech enhancement, or more generally audio source separation, corresponds to supervised method. So let's compare with one of them. Here we used OpenNMix, an open source supervised method based on a bidirectional LSTM network. This method was originally proposed for music source separation, and it was later adapted for speech enhancement by training the same network on the voice bank demand dataset for speech enhancement. We see that the performance with this supervised method is actually lower than the performance obtained with the semi-supervised methods. It can be explained by the fact that the test dataset is quite different compared with the training one. So we decided to retrain OpenNMix on the QUTW SJ0 dataset, which contains 25 hours of noisy speech and clean speech pairs, with the same noise types and SNRs as for testing. We see that clearly retraining OpenNMix in order to have a match between the training and testing conditions helps. In the end, we observed that the proposed semi-supervised method based on the variational inference with a recurrent variational autoencoder obtains slightly better performance compared with the supervised method, but we have to admit that state-of-the-art supervised method for speech enhancement currently use much more training data than the 25 hours we have used here. One of the main limitations of the semi-supervised methods is the computational time. The approximate posterior inference techniques that are involved in these methods are slow. The MCMC approach is slower than the variational one, which is itself slower than the map one. Actually, for the most complex model and the most complex technique, it can take up to 10 times the duration of the signal to process it. Some solutions have been proposed to deal with this computational complexity issue in the literature. In this paper by Manuel Pariente and co-authors, it was proposed to extend the set of latent variables in order to develop an efficient variational inference method that leverages the already trained VAE encoder. More recently, it was also proposed to use an inference model trained in a supervised fashion from noisy and clean speech pairs. So now, to illustrate a bit more the interest of semi-supervised approaches, we are going to see with an audio example how these speech enhancement methods that we have discussed so far generalize to another task, which is singing voice separation. So from a music mixture, the goal is to separate the vocals from the accompaniment. So the vocals play the role of the speech and the accompaniment of the noise. We qualitatively compare three methods. The OpenNMix method for speech enhancement trained on the QUTW-SJ0 dataset. So we have a mismatch between the training and the testing condition. We will also compare with OpenNMix, but this time trained on a dataset for music source separation, actually for singing voice separation. So we have a match between the training and the testing conditions. And finally, we will compare with the proposed method, which is based on a variational EM algorithm and using the non-causal version of the RVAE model. So this is a semi-supervised method developed for speech enhancement. And the RVAE model here was trained on speaking and not singing voice. So this is the musical mixture that we want to separate. Si tu cherches un peu de gaieté, viens donc faire un tour à l'embé. And now I will play the estimates of the vocals with first open and mix trained for speech enhancement, then open and mix trained for singing voice separation, and finally the proposed semi-supervised method for speech enhancement.
Si tu cherches un peu de gaieté, viens donc faire un tour lambé. Si tu cherches un peu de gaieté, viens donc faire un tour lambé.
So we have heard and we can actually observe from the spectrogram that a lot of the accompaniment is in the vocals estimate for open and mix when it is trained on a speech enhancement dataset. Open and mix trained for singing voice separation and the proposed semi-supervised speech enhancement method obtain much better results. We can also listen to the estimates of the accompaniment.
Si tu cherches un peu de gaieté, viens donc faire un tour lambé.
It leads basically to the same conclusion. The point here is not to say that you should use the proposed method for singing voice separation. You should definitely use open and mix trained for singing voice separation. It's just to show that semi-supervised methods have interesting generalization properties compared with supervised methods, which sometimes have difficulties for generalizing to data that are different or tasks that are different compared with the training setting. Let us now conclude about this application of the VAEs for speech enhancement. Evaluating deep generative models is difficult, and we believe that using them as priors for solving inverse problems, for instance here speech enhancement, can be useful. Deep generative models such as dynamical variational autoencoders also offer a principled way of developing weakly supervised methods. For instance here we only learned a clean speech prior based on the DVAE. This weakly supervised approach offers some kind of flexibility. For instance, here the noise model was adapted at this time, which allowed the speech enhancement method to perform reasonably well for singing voice separation, but more generally, this is useful when there is a risk to have a mismatch between the training and the test conditions. But this flexibility is not free, and we have seen that the semi-supervised speech enhancement method based on DVAE is computationally demanding. So when there is no mismatch or when a sufficient amount of training data is available, clearly the state of the art corresponds to supervised methods, which are better and faster. For instance, you can see this amazing PyTorch-based audio source separation toolkit called Asteroid, developed by Manuel Pariente and colleagues. Probably the most interesting perspective here would be to develop a true semi-supervised speech enhancement method by learning from both labeled and unlabeled datasets. We believe that deep generative models, and in particular here dynamical variational autoencoders, are promising for this. I will now let Laurent conclude about dynamical variational autoencoders.